Hello friends, let us continue the second part of work energy theorem and its applications. Next case. For a system consisting of many bodies, we know that work is equal to change in kinetic energy. So, in order to apply work energy theorem to the system, step number 1, you have to identify the forces acting on the system. Once the forces identified, calculate the work done by all the forces. Work done by gravity, work done by friction, the normal force, etc. etc. So after calculating the work done by each force individually, calculate the net work done by all the forces. We have to use the work energy theorem. Net work done is equal to change in kinetic energy. This is how we have to proceed. To start with, let us take the first example. Calculate the velocity acquired by the body on reaching down the smooth inclined plane of length L. So how do we calculate the velocity acquired by the body, this particular body of mass m, on reaching down the inclined plane here? It is a smooth inclined plane of length L. Here is a body of mass m. It is starting from rest. Our aim is to calculate the velocity using work energy theorem. How to solve it? From work energy theorem, we know that work done by all forces, W is equal to delta Ke. How many forces are acting here? You can just see very clearly. Weight of the body always act down. Normal force always act normal to the surface. And of course there is no friction. It is a smooth inclined plane. The work done by the normal force is 0 because the displacement and the normal force both are perpendicular. In this particular case, the normal force is acting this way and the displacement of the body is along the incline. So the work done by the normal force is 0. So what is the work done by the weight? For that, you need to resolve the weight into two components. One is mg cos theta, which balance the normal force, and the other one is mg sin theta, which is along the incline. So this mg sin theta is the component of force along the inclined plane. Of course, mg cos theta is not doing any work as it is also perpendicular to the displacement. Therefore, what we can write is work done by the normal force is 0, since the normal force is perpendicular to the displacement. So what is the work done by the gravity is equal to the force in the direction of displacement, mg sin theta, into displacement in that direction. Therefore, from work energy theorem, therefore, what is the net work done? Work done by the normal force, work done by weight is equal to simply mg sin theta into L. Now you can apply work energy theorem. According to this, net work done is equal to change in kinetic energy. What is the net work done here? Only by weight. Mg sin theta into L is equal to final kinetic energy on reaching down is half mv square. Initially it is at rest, therefore initial kinetic energy is 0. Velocity acquired by the body is square root of 2gl sin theta. That is the answer to this. In another manner, how can you do it? You can also do this by applying Newton's laws of motion. If you see the diagram, it is very simple. Weight of the body is acting down, normal force is acting this way, and this mg cos theta, one of the components, is balanced by normal force. The unbalanced force is along the incline mg sin theta. So what is the net force here? Net force is equal to mg sin theta. Hence acceleration is equal to net force by mass, that is g sin theta. What is the velocity acquired by the body on reaching down the plane? We know that v square minus u square is equal to 2as. Here u is 0 starting from rest. So v square is equal to 2. What is acceleration? G sin theta into displacement is L. Hence you got the equation v is equal to square root of 2gl sin theta. Okay. This is how you got the same answer by using Newton's laws of motion. If friction is present, how do you do it? In the above example, if it is a rough surface, that means mu is not equal to 0, find the velocity. Find the velocity. How do you do it? Very simple. How do I calculate the velocity? The frictional force also present. This is a rough inclined plane of inclination theta. Everything is same. And here it is a rough surface. Rough surface means what? Here the coefficient of friction is mu. Therefore, friction will try to oppose the relative motion. Here from work energy theorem, we can say that work done is equal to delta K. This we know. Here how many forces are doing work? We already know that work done by normal force is 0 and only work done by gravity and work done by friction. So the component of force along the displacement is mg sin theta. Therefore the work done by the gravity for the displacement L will be mg sin theta into L. Friction by nature, it opposes the relative motion. As the body is moving down, friction is doing work, but it is doing a negative work. Force and displacement are opposite. Work done by friction is equal to minus of frictional force into displacement. So frictional force is mu into normal reaction into L. What is the normal force here? Normal force is equal to mg cos theta. When this is theta, this is also theta. This will be mg cos theta. Therefore, work done by friction is equal to minus mu mg cos theta into L. Only these forces are doing work. Therefore, net work done by all the forces. Work done by normal force, work done by gravity, work done by friction. Yes or no? Is equal to change in kinetic energy. Right? What is the work done by normal force? 0. Work done by weight is mg sin theta into L. Work done by friction will be minus mu mg cos theta into L. mgl into sin theta minus mu cos theta. Here you can write mu k also because the body is sliding. Therefore, from work energy theorem, what we can write? Net work done means what? We just now calculated. mgl sin theta minus mu cos theta is equal to change in kinetic energy. That is equal to final kinetic energy minus initial kinetic energy. Initial kinetic energy is 0. Let us say the final kinetic energy is half mv square. Why? Because let v be the velocity acquired by the body on reaching down the plane. So what you can write here? Half mv square minus v. So here m gets cancelled and you are left with velocity v is equal to square root of 2gl into sin theta minus mu cos theta. Here mu means you can write mu k also because the friction involved here is kinetic friction, where L is the length of the incline. Okay? Yes. A particle is projected in gravity with a speed u. Find the speed of the particle as a function of vertical displacement. See, this is the projectile motion we are already familiar with. But we have to apply the work energy theorem to solve it, right? So what is work energy theorem? Here the only force which is doing work is the gravitational force. No other force is acting because air resistance is neglected. What is work energy theorem says? It's here who is doing work? Work is done by the gravity. So work done by gravity is equal to, what is the work done? Work done by gravity is negative because gravity is acting down but the body is moving up in the beginning, right? Gravity always act down but the body is moving up. Therefore, let us write the displacement. Displacement is in the upward direction. Gravity is acting down. So what we can write here is displacement in the upward direction. Why? Because when the particle moves along the trajectory, parabolic path, at any instant of time, let us suppose that it is at the point 2. Here, the vertical displacement is y. So work done by gravity means how much? As both are opposite, I will write minus mg into displacement y. Clear? So now this is the only work done. Therefore, work energy theorem you can take now. From work energy theorem, work done is equal to change in kinetic energy. Initial velocity is u, therefore initial kinetic energy is half mu square. Final velocity at the point 2 is v, therefore final kinetic energy is half mv square. Direction is not a matter because you are squaring the velocity. Minus mgy. Work done by gravity is minus mgy. Minus mgy is equal to ke final minus k initial. Half mv square minus half mu square. If you take minus, what you can write is u square minus v square. So you can write gy is equal to 2gy is equal to u square minus v square. Therefore, v is equal to u square minus 2gy. This is the velocity acquired by the body at that instant. If the point 2 is above, the point 2 is above the point 1, then displacement y will be positive. If the point 2 is below somewhere here, let us say, then displacement will be negative. If the point 2 is taken somewhere below here, then displacement will be negative. If the point P lies above, y will be positive. So here note point, if the point 2 lies below 1, then v will be equal to how much? Square root of y will be negative, na? You will have u square plus 2gy. In another manner also you can do it. How do you do it? We all know that use the equation v square minus u square is equal to 2as, and you can obtain the same formula by using one-dimensional motion equations or two-dimensional motion equations. So without applying work energy theorem also you can solve it by using that. Same result you can. We already learned it in two-dimensional motion or projectile motion equations. Thank you. See you later.